I will be presenting a study titled Effect of Injection Rate on Coke Dust Formation and Coke Gasification in Blast Furnace Shaft. So, the motivation of this research stem from a major economic challenge in steel manufacturing. The high price of metallurgical coke. To reduce cost, steelmakers are increasingly injecting auxiliary fuel like heavy oil into their blast furnaces. However, in finish furnaces, an interesting side effect was observed. When oil injection rates were high, the amount of carbon rich dust in top gas increased. This is a concern because higher fuel injection means coke inside furnace is exposed to mechanical stress and chemical reaction for longer period, which can degrade its quality. Maintaining good coke quality is absolutely critical for furnace to operate efficiently. Degraded coke break down into a fine particle which harm the furnace's permeability, increase pressure loss, and can lead to material being blown out of the furnace with the top gas. So the primary objective of this study was to understand how different oil injection rates affect coke gasification and the formation of fine coke dust under simulated blast furnace condition. To do this, the researchers used a blast furnace simulator. They took coke pieces and gasified them at temperature up to 1400 degrees Celsius. The key part of the experiment was creating different gas atmosphere that simulated heavy oil rates of 0, 100, 120 and 135 kilograms per ton of hot metal. A higher oil injection rate means more hydrogen and water vapor are present in the furnace gas. After the gasification process, the coke pieces were put through a mechanical stress test using a programmable shaker sieve to measure how much fine coke was generated. Finally, they used BET surface area analysis to determine how the coke was breaking down, whether the reactions were happening just on the surface or throughout the entire piece. To understand the result, we need to look at the key chemical reaction known as solution loss reaction. This reaction consumes the coke and typically start around 900 to 950 degrees Celsius. There are two main reactions. First, solid carbon from the coke react with carbon dioxide to produce carbon monoxide. Second, carbon react with water vapor to produce hydrogen and carbon monoxide. Injecting oil introduces more hydrogen, which leads to more water vapor in the furnace gas. It is important to know that reaction with water vapor has been shown to be faster than the reaction with CO2 at the temperature found in the blast furnace shaft. Now for the result. At temperature up to 1100 degrees Celsius, the impact was significant. First, higher simulated oil injection rates, meaning more water vapor in the gas, led to much faster overall rate of coke gasification. The coke was consumed more quickly. Second, and more importantly, the coke that was gasified in these water vapor rich atmosphere produces significantly more fine coke dust when put under mechanical stress. This strongly suggests that higher oil injection weakens the surface of the coke. The BET analysis revealed why this happens. With more S2O, the reaction was concentrated on the coke's outer surface. In contrast with only CO2, the reaction occurred more evenly throughout the entire coke pieces. So when the researchers pushes the temperature up to 1400 degrees Celsius, the story change. At these very high temperature, the difference in gasification rate between different atmospheres becomes small. The amount of water vapor was no longer a major factor. Similarly, the amount of fine coke produced was also less varied. The likely reason for this is that such high temperature, the reaction is no longer limited by speed of the chemical reaction itself, but by how fast the gas can diffuse to coke surface. Because of this diffusion limit, the reaction happens on the surface regardless of the gas composition, leaving the inner core of the coke intact. So, what does this all mean for the blast furnace? The key implication is that the gas atmosphere changes how the coke degrades at low temperature. With high oil injection, the water vapor reacts aggressively on the coke surface. This creates more fine dust that can be carried away by the gas, but it may leave the core of the coke pieces strong. Without oil injection, the CO2 reaction penetrates deeper, weakening the entire coke pieces from inside out, which could cause it to lose strength later on, deeper in the furnace. Furthermore, increased oil injection could cause this solution loss reaction to start happening higher up in the furnace shaft, which might also impact the iron ore reduction process. So, to conclude, this study found that below 1100 degrees centigrade, increasing oil injection rate accelerate coke gasification and increase the formation of fine coke dust by concentrating the chemical attack on coke surface. Above 1100 degrees centigrade, the effect of oil injection rate on both gasification and fine coke formation is small as the process becomes limited by gas diffusion. The main takeaway is that higher rate of oil injection can indeed increases the amount of fine coke dust generation in the upper part of the blast furnace shaft, and these same effect could be expected when using other hydrogen rich injectant such as coal dust or natural dust. Natural